Hi, everyone, and welcome to part 11 of the Block 74 Apollo Guidance Computer Project. Today is going to be part one of the X register. Now, the X register is a bit different compared to a number of the other registers that we've looked at. Um, in the last episode, we talked about the Y register, which is one of the two operands as part of the arithmetic unit, which is the adder within the guidance computer. So the X register is the other operand. So basically the two words that get added together to perform various math operations, and how the adder is used um, in, depending on the particular instruction, can be used to also create multiplication, division, subtraction with the use of the other registers and various control pulses. But you can see here that we have this, the WY, which is our write in. So we can write in data into the Y register from our write lines. But we don't see, there's no WX control pulse along here. And in fact, we have this little, you can see on this little diagram, we have this little +1, -1, +2 to register X, which goes into the logic unit. And this is because the X register doesn't really have the same input capabilities that the Y register has. So we'll talk a little bit about that as we go into the kind of input command. So what I'm going to do is I'm going to kind of break the X register into a couple of episodes. So today we're going to talk about more how does data get into the X register and the various control pulses that kind of operate that. And then in the next episode, we'll more talk about how does the adder work, because at least in how I'm implementing it, the adder is going to be closely tied to the X register. And then the outputs of the adder have some additional complexity. So one, they're similar to the A register that we talked about a few episodes ago. So it does some of that or logic with the right lines in some of the control pulses and the sequence of control pulses. And then it also is used to write data into the G register in certain scenarios as part of the storing data back into and out of memory. But back to the X register. So we can kind of see here that X and Y are part of the arithmetic unit that we just talked about. And this is some of the details we talked about in the Y register. So they mentioned the X and Y register are similar to the other flip-flops. However, the write service is more complex for register Y. So we talked about that in the last episode about register Y. So it mentions why register Y is written into from the write lines, but register X is not. So the quantity entered to X is by control pulse action or the write line A2XG. So that's a control pulse that basically will transfer data from the A register directly into the X register, not going through the write lines. So we can kind of see this is they're generated to write into register X during extra code instructions and the add instructions as well. Now, there are a few other sort of command pulses or control pulses that will write data into the X register. So we talked about A2X. Then there's this PONX, which is +1 into X, which will load X with octal value 00001. So it's basically just going to load it with the value 1. Then there's also MONX, or -1 into X, which is going to load X into octal, in this case, 1777776, which is 1's complement for -1. We also have this 2X, which is +2 into X, which is to load X with octal 00002. There's also another B15X, which is to load X with octal 04000, which is actually basically flipping bit 15 or setting bit 15 of the X register. And as mentioned, there is no WX control pulse, so this doesn't actually read or doesn't write data from the write lines into the X register. We also have some of the control pulses that we talked about in the last episode for the Y register that has some kind of impact on the X register itself. So whenever we get a WY, a WY12, or a WYD control pulse, we also need to clear the X register and the carry bit. So we'll talk about the carry bit in the next episode where we talk about the adder, but we do have to make provisions that these control pulses will also clear the X register. So let's look a little bit at the kind of schematic of how we've designed that for the X register. So see, this is a bit more complex because of the adders and stuff that are on the right side over here, but we'll talk about that in a later episode. So we'll focus here on kind of this section of the kind of the schematic and circuitry. So we have the various pulses we talked about. So these are all kind of ways data can be written into the, we've got A2X, we got the WY, WYD, and WY12. Now, there's one other control pulse that we haven't talked about. It's the CLXC, which is a control pulse that basically, if BP, which is the the branch register. So there's two branch registers that are used for program control, and if the CLXC control pulse is asserted and BR1, so the branch register 1, is set to 0, we will clear and reset the X register. So you can see that it's clear X register is kind of the control pulse. So what we'll do first is we'll just talk about the kind of the circuitry to reset or clear the contents of the X register. So we have basically this logic where we say, hey, if we have any of these pulses or this combination of these two pulses that we bring together, and then we also have our general reset. So if we want to press the reset button on the computer to basically clear out everything, we have this signal coming in, and that's all kind of combined together along with our basically our read timer. So basically we'll clear this out when our read time pulse comes through. And that basically we generate kind of two of these reset signals. One of them that's going to actually reset all of the register contents. So set X to 0. And then we also have this second one, which actually will go out into our CI, which is our carry register. And again, we'll talk more about that in the next episode. And that's because while the WY, WYD, and WY12 clear the X register and the carry bit, this combination, the CLXC and the branch 1, only clears the X register. So that's why we kind of have to break it out to basically the logic between when do we clear the register and when do we clear the carry bit. So that kind of takes care of our logic for the clearing of the register. And then we have our logic here around when do we load the data into the X register. So we have our P1X, our -1X, our P2X, and then a little bit down here we have our B15X here. So we have our 2-to-1 selectors. So we have 4 of those 2-to-1 selectors, and we have kind of option 1, which is where we load from the A01. This is sort of where we load from the A register, and that's with our A2X. So that's kind of how we're going to use this selector. And then we have the combination of the whether we get one from the P1X, the -1X, the P2X, and then the B15 that's a little bit further down. So 2 things that happen. One is we want to generate our enable pulse so that we can load that data into the actual X register. So this is our 74LS173's 4-bit D registers that'll actually store the data. So we have our logic kind of up here where we combine it with the A2X pulse is one option. And then we also NOR that with logic that comes, you can kind of see from here, from the logic that we get from our, whether we have one of these asserted, the P1X, -1X, P2X, or B15. So basically, if either of those scenarios occur, we're going to use that to enable our write-in. And then we have our selector that we use to say, hey, if it's if none of these are, so if basically the A2X is asserted, we will load from the A register. If one of these others is asserted, then we'll kind of load from the second option within our 2-to-1 selector. And then the rest of the logic here is to kind of generate the appropriate values for that second option. So if it's a P1X, it's pretty simple. Again, because it's negative logic, we just invert that. So if this goes to 0, we turn this into a 1, and we load that into the first bit of our register. So that'll give us logic 1. For the P2X, it's a little bit more complicated. So again, we invert it because of the negative logic. And then we have an OR because we want to set this bit to be 1, either if we have the P2X signal, or if we have a -1, because in the case of a -1, basically the first bit will be set to 0 and everything else will be set to 1. So that kind of gives us the option of, if it's a P2X, we'll set this bit to 1 and everything else to 0. If it's a -1X, we'll set this one to 1 and then everything else to 1 as well. So that's to set all the other ones to 1. That's where these inverters come in here, because we'll have to set every other every other input to 1. And I'm using 2 inverters here just for fan out reasons. So we actually will have to load 16, and with the 74LS logic from the data sheets, to say kind of 10 fan out is kind of the ideal. You don't want to go, if you can avoid it, you don't want to drive more than 10 inputs with the output of a single gate. So we basically will use 2. So the first will basically drive the first 8, and then the second will drive the second 8. And then we have this one other scenario here for our B15X, which is where we want to set bit 15. And again, we use that same kind of OR logic that we did with the P2X in order to load that. And then from there, whatever we select is loaded into the X register itself. And all this to the right is where we start getting into the adders and carry registers and some of the clocking that we'll have to deal with for that, the kind of ORing on the right buses that we'll talk about in a later episode. I'll pop up the simulator and just kind of take a look at how we've implemented the logic. So I'll just kind of look at the reset. So again, we've got our options here. I'm just going to turn off, zoom in a little bit. This is our kind of reset signal for the X register and reset signal for the carry bit. So we have this to say, okay, well, if I've got a WY pulse and then we have a reset, we can see that that's going to set the reset pulse on both the X register and carry bit. And that's kind of the same logic that'll work for any of these other options. And then we have this scenario where if we have the CLXC control pulse and BR1 is set to 0, we will only clear out the X register. So you can kind of see the difference there. And then we have our general kind of reset button that if we hit that, everything gets reset. Now, so that kind of takes care of the reset logic. And now we have our kind of write logic for loading data in. So we have here, if we have our A2X, so we're going to assert that. That means this is our kind of write control for when do we enable the registers to load data. And again, it's negative enable, so this goes to 0 versus the reset, which is actually reset on positive pulse. So in this case, if we go to 0, basically we've asserted the A2X signal. We're going to assert our write, and we'll have our selection value to 0. So that means it will pick out the A register inputs for the X register. If we have a P1X, I can click that. And once that's asserted, we can see our selector changes, so that we're now selecting the opposite inputs on those selectors. Again, are asserting 0, so we're enabling the D registers. And then if we look at kind of our logic here, we've set bit 1 to 1, everything else to 0. So this is going to load the X register with the value of 1, which is what we want in that case. For the P2X, kind of similar, I will click this here. Now we set this to 0, and now we've got everything 0, but we've got a 1 going into bit 2. And then for the -1X, I'll click that, and we can see, okay, now we're loading the -1 here. And then for the B1X, we'll click that, and we can see we're just loading that into the X15 bit. So that kind of takes care of at least how data gets into the X register. I'm not going to go through the kind of bill of materials yet for the X register, because there's a few more episodes we're going to have to go through in order to kind of provide the combined design of the X register, including the adders and the bus logic. This is the first board. So as I mentioned on an earlier episode, I've ordered some new register boards, and I've made them actually a bit bigger so I can put more chips onto them, because the X register, when I was doing the initial design, was getting very, very close to the maximum number of chips I could fit on my existing boards. So I've made it bigger so I can hold more chips for the X register, as well as the G register is quite a bit more complex as well. And the S register, which also will contain our memory, also needs some additional real estate. So those should be arriving in the next week, and then we can start getting into the construction of the X register. Made good progress over the past week in building out my L register, A register, and Y register. So those are just about done. And in the next episode, actually at the beginning, show you some pictures of how those are coming along. Anyways, thanks for joining. Again, if you're interested in seeing or continuing the series as I keep building this out, definitely subscribe so you get notified when a new episode comes out. And as always, love to hear anyone's comments. If you have any feedback, any suggestions, things you'd like to see more of, please let me know. And until next time, we'll have a good rest of the week.